In this video, I'm going to be going over building another do-it-yourself 3D camcorder. But first, let's take a look at why we would even want to record in 3D. It's admittedly kind of a novelty. You don't have optical zoom and focus is fixed. In that respect, it's kind of like the olden days of shooting on motion picture film with prime lenses, granted without focusing capabilities. What I'm doing here is a hundreds of dollars option as opposed to the thousands of dollars option where you'd likely find sophisticated camera controls. Speaking of which, exposure and white balance are also all automatic in this solution, and the cameras are also far from high dynamic range. That said, it can be a neat way of documenting something and watching later with additional 3D immersion with video for each eye. To watch 3D content, you'll need a VR headset, a 3D TV, Google Cardboard or similar product, or you can even process the footage with FFmpeg into an anaglyph and watch with 3D glasses on a 2D display. When watching 3D content on a VR headset, I can at least speak to doing so on a Meta Quest 3. You can watch the videos, assuming they're re-encoded in a web-friendly format like WebM, in the Quest web browser. You can download the videos and watch offline using the Quest web browser, referencing the local folder the videos are saved to, or you can use a third-party app to view the videos. I bought the Skybox VR app and it seems to work pretty decently for that purpose. Alright, back to the walkthrough. So I'm going to be basically building a replica of this, with some improvements here and there. So let's go over the hardware on this. So the computer running the show here is a Libre Renegade, a 4 gig version. We have this PCB with some buttons soldered onto it, and wires going off to the power pin on the Renegade, as well as GPIOs for a program that I wrote to control that program. We also have a USB flash drive here. This is what footage gets saved to. We have a microphone right there, a mono microphone. And then this USB stereoscopic camcorder. Now it connects via USB-C and then USB-A connector into this USB 3.0 port on the Renegade. The Renegade has two USB 2.0 ports and one USB 3.0 port. I found that you need to have the USB camera connected to the USB 3.0 port, otherwise you'll get dropped frames. I have a battery pack here. This particular one is a 10 amp hour battery pack, USB battery pack. I have this special shorter USB-A to micro USB cable just so I have less cable clutter on this unit. You can just power it on just by hitting the power button here. As for these other buttons that are wired to the GPIO, this is the record start stop button. This is the frame rate 30 or 60 frames per second toggle button. And this is the microphone enable disable button. So when the microphone is actually taken out, the microphone will always be disabled. The program checks for the presence of the mono microphone when it boots up, and if it doesn't find it present, it will just make sure the microphone is disabled, so that when FFmpeg is called to record the footage, it's not going to be attempting to record audio. The C program that I wrote that starts up when the unit boots up is simply just making calls to FFmpeg to record footage. Now it's recording to a RAM drive. We see here this is a 4 gigabyte version of the Renegade. I found that when I record footage directly to a USB flash drive, I'm getting dropped frames. So the solution was to just create a RAM drive when this thing boots up and just save into that RAM drive, and then when the recording stops, you can then move that video file from the RAM drive into the USB flash drive. Now that process of moving that file from the RAM drive into the USB flash drive does take some time. That is one of the inconvenient aspects of this, in that when you record something like, say, 2 minutes long, you stop recording, it might take 2 or 3 minutes to move into that flash drive. We also have this voice recorder I velcroed on, so it's going to be recording stereo video and then stereo audio separately. There's a mono mic also recording audio so that you can easily synchronize the stereo audio with the video with that mono track. Parts used here are the Libre Renegade board. Again, 4 gig version. The 2 gig version will work, but you'll just have a lower duration of video you can record. With the 4 gig version at 60 frames a second, full resolution, which is 3840 by 1080, 1920 by 1080 for each eye. With the 4 gig version, what I'm doing is I'm creating that 3.5 gigabyte RAM drive. That's about enough storage space for 3.5 minutes of footage. So we have the SD card for the operating system. We're not using the SD card to save footage, so I could actually go with a smaller sized SD card maybe like an 8 gig if I can find one. Our battery pack here. Now this is the 10 amp hour battery pack. This one here is 5 amp hours. This was the pack I originally got. I had some issues that I thought might have been power related, so I got this 10 amp hour pack. But it turns out the issues that I think it was having were maybe a bad connection, a USB connection, or maybe the disk being full. So this 5 amp hour pack I'm going to use in this rebuilt version. USB mic here. Again, it's just a mono mic. It's okay for just general audio, but if we're going to be recording stereo video, we might as well record stereo audio. It would be silly to not record stereo audio. I couldn't find any stereo USB mics. I suppose I could have just rigged up 2 mics, maybe even with a USB hub, but this audio recorder is pretty decent. Even though it records in Windows Media Audio, you can always convert that and just bring it in when you're editing. USB flash drive. So the USB flash drive gets mounted at boot, and then it gets saved to when the footage is done being recorded. The footage gets moved to that flash drive. I wanted to have removable storage in this form factor just so that it's convenient to take the drive out, plug it into a video editing workstation, and work from it there. I didn't want to have to be connecting via a network to pull the footage off. I didn't want to be saving by default to the SD card. That makes it a nightmare to pull that footage off. I just want to save it to removable storage so I can just easily yank out, plug into a video editing workstation, and just take the editing from there. This is the camera mount. So the camera module slides in here. It attaches with M2 screws with nuts. And I have this 1/4 inch nut, 1/4 inch being what's used on tripod mounts. So in this case I'm using it to attach into this corner brace like so, but I also wanted to use this type of nut so that I could use it with a head strap that also uses a tripod screw. There's also a hole there so that you could mount in this other piece. If you have a right angle magnetic USB-C connector, for having this whole piece head mounted, you have a right angle connector. I wanted to hold it in place so it doesn't damage the USB-C port. So that's what that piece is right there, held in place by an erector set screw. Now I have some erector set parts in here that I use for prototyping. Primarily this metal piece here for serving as a standoff for the battery pack. In the updated version I'm going to be making, I'm going to be using all 3D printed parts I design in OpenSCAD and print out on my 3D printer. The erector set pieces on this prototype right now are here. I have an erector set screw there, which I'll keep. And then I have some erector set pieces there, and there for the standoff for the Renegade board. I'll be printing off my own standoffs for the board here. And these rubber washers here, I'll be using 3D printed plastic standoffs for those as well. I also have some rubber washers here for the screw holding the camera mount on the corner brace. Other 3D printed parts I have, there are these small plastic pieces that hold the board a little bit better in place there. I needed to do that because the holes on this camera on the PCB are really close to this plastic enclosure for the camera, and there just wasn't enough clearance for the head of the screw, so I needed to design and print off these plastic pieces that kind of sandwich the PCB, and then you have an M2 screw with nuts holding it in place. Kind of a fragile design, but it works. I also got this special USB-C to A short ribbon cable from a seller on Amazon. It works really well. That way I don't have cables coming off this way and up this way on this end. It makes it nice and neat cabling wise, and it also doesn't get in the way of pressing these buttons. When the board boots up, the power LED, which is the red LED, turns on, and the green LED is for disk activity. That will flicker as it boots. But when the C program that I wrote starts up automatically once everything is booted up, those LEDs are turned off and they're instead used by my C program that's running the show. When you press the record button, the red LED will turn on, indicating that it's recording. When you press the stop button, the start-stop button again to stop recording, the red LED will still stay on, but the green LED will come on, indicating that it's busy copying, or rather moving footage from the RAM drive into the USB flash drive. And when those lights go off again, it's back into a ready state. I also use the green LED to communicate any error states. If it gets into an error state, the green LED will turn on and stay on. And the microphone on-off button, as well as the frame rate toggle button between 30 frames a second and 60 frames a second, when those buttons are pressed, the green LED will blink once, indicating 30 frames per second or microphone disabled, or it will blink twice to indicate 60 frames a second or microphone enabled. And we're talking about this microphone here because the audio recorder is totally separate. To turn the system off after it's on, you can either press the power button here, or you can press the red wire button and the yellow wire button together and release. When you press these two buttons together and release, the green and red LEDs will alternate blinking, and then the system will proceed with shutting down. This is the preferred way of turning it off, because if you just press this power button, the LEDs are already going to be off, so the only way to know that it's turning off is if you look carefully at the power LED, which is off, it'll flicker really quickly, indicating that it's off. As for the operating system, this system is running Libre Computer's own Raspbian OS or Raspberry Pi OS that is set for the Renegade board. So I use that as my base, and then I have my C program that I write, compile. I have some other components needed like FFmpeg, some other software components. And then the C program is compiled. It is configured to run on boot. Also, the RAM drive is set up at boot as well. This is the 4 gig version. I'm allocating a half gig of memory for the C program and FFmpeg, and the other 3.5 gigabytes I allocate for the RAM drive to be storing footage. And when you stop recording, of course, you have a bit of a wait for it to move that footage from the RAM drive into the USB flash drive.
Now we're on to the build slideshow. I cut a piece of wood for the base. It's 7.5 inches by 3 inches by 0.75 inches. I'm centering the corner brace on the wooden base. And as we see, I switched to metric here. Metric is just a way to go for this build. I've marked where I'll be drilling pilot holes for the corner brace. And here we have pilot holes drilled for the corner brace. The corner brace has been mounted with number 10 3/4 inch wood screws. Doing a board placement mock-up, I have the button PCB on the right and the Renegade in the middle. And we have a closer look at the board layout and where I'm going to be drilling pilot holes. I'm actually going to be centering the Renegade right over the corner brace. Also determining the heights of the standoffs for the button PCB as well as the Renegade. I like to use paper templates when determining where to drill pilot holes, so I fired up Inkscape, and that outer box is the base, and the two inner boxes indicate where to drill pilot holes for the Renegade as well as the button PCB. Here I have the paper template all printed out and ready to cut out and place over the base, and then to use a ballpoint pen to indent where I want to put those pilot holes. Here I've fired up OpenSCAD to design the standoffs for the Renegade and the button PCB. Now I need to make sure that the Renegade clears that corner brace, as I don't want that metal corner brace to be shorting out anything on the Renegade. The standoffs will be used with M2 screws. The smaller standoffs for the button PCB were quite small and nearing what my 3D printer is capable of. Now comes the fun that is the button PCB. I've taken 4 tact switches. I ran some copper wire for the ground, and then I took DuPont wires and soldered those in. Blue is for the power button, green is record start stop, yellow is frame rate select, either 60 or 30 frames per second, red is microphone enable disable, and black is ground. Using my helping hands there to help with soldering. The solder job, not exactly top notch, but it does the trick. And also using a multimeter to check the buttons. Now I'm on to designing the battery standoff. I replicated the dimensions of the metal erector set standoff I made for the last prototype. I designed the new standoff in OpenSCAD and made the pieces fairly thick and rugged, as the battery is heavy and needs to be secured decently. The battery will be secured to the standoff with a couple of zip ties. To place the battery standoff, I needed to update my paper template. The battery standoff is secured with 4 number 6 3/4 inch panhead screws. I had to be careful not to over tighten the screws due to the way the models were printed, biasing layer strength for the zip ties securing the battery as opposed to for strength of the screw holes. I also needed to design a bridging piece to connect the two standoffs together for added reinforcement. I'll also wrap rubber bands around that bridging piece to push against and better secure the battery pack in place once zip tied in. Next, the camera mount needs to be dealt with. I designed a camera mount piece that the camera PCB will mount to. The camera mount also supports the two lenses. This time-lapse of the design of an older version of the mount shows how it was crafted in OpenSCAD. Here is a time-lapse of the slightly newer design being printed on my 3D printer, an Affinia H480. I also needed to refine and print out some standoffs and plastic gripping pieces to better secure the camera PCB to the mount. The camera PCB is secured to the mount with M2 screws and nuts. The camera mount is then secured to the metal corner brace with 1/4 inch 20 screw and nut, with some rubber washers inserted to help secure it. The nut the screw attaches to cleverly slides into a cavity in the camera mount piece. Everything is relatively in place now with the camera mounted and connected to the Renegade, as well as the battery pack connected to the Renegade.
Here's the finished product. So we got the camera mounted on this mount piece. Short ribbon cable, USB-C to USB-A installed. Have some rubber washers here to help keep the mount snug and level once it's set. These plastic pieces to grip the camera PCB to the mount piece. We have an M2 and then a nut at the end. There's actually a little washer that I 3D printed in there as well, kind of sandwiched between everything. There just really isn't a whole lot of clearance to have a screw go all the way down, so that's why this standoff piece and gripping piece is there. I took the SD card from the other one I built, imaged it, and then cloned it to another SD card, and everything works just great. So we'll power it on. Now on this battery pack, I have to actually turn the battery pack on, and then it's starting up here. We have red LED for power, and then eventually the green LED will turn on, indicating that we have disk activity. The OS is being loaded from SD card. Take the lens caps off while I'm at it. There's our green LED activity light. So booting has begun, and when the lights turn off, we are ready to record. So to record, well, first the frame rate is set right now to 60 frames per second. If I press and release the yellow wire button, the green light blinked once, indicating now it's in 30 frames per second mode. If I hit it again and release, it blinked twice. Now it's in 60 frames per second. Microphone is enabled now. If I press the red wire button and release, blinked once. If I hold and release again, it blinks twice, indicating the mic is now enabled. Now I'm ready to record. I can press the green wire button, and red LED indicates it's recording now. And if I press the green wire button again, the green LED comes on, and then both LEDs turn off, indicating it's finished moving from the RAM drive into the flash drive. So now let's turn the system off. I press the yellow wire button and the red wire button at the same time, release. The two LEDs alternate, they turn solid and they turn off, indicating now the system is off. So now I can carefully remove the flash drive, and we can see the contents of the flash drive. And if I press the green wire button again, click, click, click.
An additional finishing touch was to add the ability to tripod mount the camcorder. I bought some 1/4 inch 20 T-nuts from a seller on Amazon and proceeded with dismantling components mounted to the base. I then worked on drilling a hole and routing out part of the base to countersink the T-nut. Finally, everything was remounted to the base. Additional refinements to the 3D camcorder include this reasonably priced stabilizing camera grip, which I found on Amazon. I added a threaded rod with washers and wing nuts to make it further rugged. The wooden base attaches to the base of the grip using a 1/4 inch screw attaching to the brass T-nut that was installed in the wooden base. I also added a piezo speaker with friction fit 3D printed holder that fits over the USB 2.0 port stack. The stereo voice recorder can velcro to the top of the grip. And just some closing thoughts with pitfalls and areas for improvement. Recording audio quality and synchronizing it with video can be a pain. It's kind of a throwback to shooting on film and synchronizing separately recorded audio. The onboard mic to record reference audio at least makes synchronizing easier. The Renegade doesn't have a built-in real-time clock, so the timestamps for the video files aren't accurate. A solution could be adding a real-time clock to the Renegade, or simply using the timestamps on the separately recorded audio if accurate timestamps are needed. Editing the footage can be quite a workflow task. I like preserving as much quality as possible, so I find myself converting the motion JPEG videos the camera generates into lossless intermediate video files, encoded with Huffman YUV and/or the Laggard lossless codec, which can make even small projects rather demanding on disk space and intermediate processing time. Scripting and conversions with FFmpeg and batch files can be handy. FFmpeg is also very handy for generating anaglyphs. Generative AI is especially helpful for figuring out needed FFmpeg commands and for scripting. I found that the cameras aren't perfectly aligned. I'm not sure if it's a manufacturing tolerance issue or if perhaps my camera mount piece is flexing the camera PCB to put the cameras a little bit out of parallel alignment. There's also slight rotational issues as well, which leads me to further believe it's at least in part a manufacturing tolerance issue, though I may need to look further into that with the 2 camera modules I have. The rotational issues can be fixed a little bit in post by translating and rotating each half of what each eye sees, though in doing so you lose image quality by resampling. I suppose one could come up with a defined set of operations per camera module to rotate and translate each eye's video to better align, though that would be additional processing when there's already a fair amount of intermediate processing needed. I have encountered issues whereby when one starts recording, then stops recording, the unit will not record, sometimes appearing to be recording, but when recording is stopped, the green LED indicating moving the recording from RAM to flash drive turns on just for a moment, and then it's observed that footage didn't move to the USB flash drive. Thus, I think there are additional glitches to work out. Ultimately, recording directly to disk would be welcome, as recording to RAM and moving the footage over can cause one to miss in-the-moment content to record. I may have to see how well a tiny USB 3.0 hub would work for allowing the camera to record to a fast USB flash drive. A tiny OLED display would be a welcome feature to add, though using the red and green LEDs on the Renegade board is at least a cheap way to communicate some device status to the operator. Build materials list, 3D models, OS setup instructions, and source code for the project are available at mikeshorts.com/MISC/3DCam.